But do note that the focus of the free online lesson today will be on how to use Inventor Nastran and not on the theoretical background of how FEA simulation works. In case some of you don't know, FEA stands for Finite Element Analysis, and it is a type of virtual testing where you see your 3D model will fail or not when it is put under stress and loading. So this is the 3D model that we will be carrying out our FEA simulation. So this is the lever in this machine, and this is the cross section of the machine. So what you can see from here is there's a loading on the shorter end. You see this end, the shorter end. There's a loading on this side where is weight, where this weight will pull this lever downwards in this position, this direction. And on these two parts, it is the fixture, where these two parts, it is prevented from translating or rotational constraint. Okay, moving on. This is what I'll be covering in today's FOL. So first of all, I'll be going through the procedure of a general design overview with you. And then I also include the procedure of the exercises on the FEA simulation that I will be going through together with you, the demo of the Inventor Nastran demo. So when you want to refer back or you want to recap, you can just go back and look at the exercises part in this slide to refresh on the exercises that I'll be covering. And then after I finish the demo, we'll be going through the result. And since FEA simulation will be, it will come up with many results such as displacement, safety factor, and so on. But due to the time constraint, and I will only emphasize on the one meter stress. So before that, this is the resources that I'd like to share with you. The data set include the 3D model, the lever that I actually showed you just now, and also this set of PDF slides. You can refer to both of it, and if you like to follow along my exercise, feel free to do so. You can retrieve them by clicking on this link. I will share it in the chat, or you can just scan this QR code and you will be brought to this link where I actually share the PDF slide and data set right there. I've sent it into the chat. Don't worry, those participants that come in later, I actually included the QR code onto every slide. You can just scan the QR code and you'll be brought to this link. So moving on, like I mentioned just now, we'll be going through the procedure. The first will be a general design overview. So in a general engineering design, first of all, you start off with idealization, which is 3D modeling, and then followed by boundary conditions. So boundary conditions will be like applying material to your, so for boundary condition, let me mention beforehand, there will be 4 things that you need to apply. The 4 boundary conditions include the first, which is applying material to your 3D model, followed by applying constraint, or what I mentioned just now as fixture, the part where depending on your 3D model, what type of a condition it is put under, it can either be restricted from translational movement, rotational movement, or both of it. And then I've said material and constraint. The third will be applying loading. That means the part that will have forcing acting on it. And finally, the 4th thing in boundary condition will be applying your initial meshing. Next will be simulation analysis. So you let the software run and then you will analyze the result. So in simulation, most of the time you have these 3 main results, which is your 1 meter stress, your deflection, and your safety factor. So you can actually identify whether your object will fail or will not fail depending on your simulation analysis. So if it fails, what you have to do is you have to go to the 4th step, which is redesign, or if you only need to actually make a small changes to your design, In other words, it will be optimization, where you actually only make small tweaks to your design so that it actually will not fail. So in the case where it actually passes the simulation analysis, we have to do another thing instead. So the other thing will be applying different meshes. So like I say in boundary condition just now, you'll be applying initial meshing. So since your result now does not fail in simulation analysis, you have to apply other meshing sizes so that you can do the convergence test on to see whether your simulation is accurate or not, and you are trying to find the most the optimal meshing size for your 3D model. So that will be our focus today. Our focus today will be on the two parts in the middle. Since I have already shared with you the 3D model from the idealization, so the idealization step can be skipped. And then we assume that our model does not need redesign and it is already in its final state of design. So we will only be focusing the two steps in the middle, which is boundary conditions and simulation analysis. So for those of you who come in late, you can scan this QR code to retrieve my 3D model and also the slide that I'm using right now. So starting from this slide and the two slides later on, it is the procedure of what I'll be demoing today. So I'll be first showing you how to create the first mesh sizing, which is of the size 2 mm, and then next 1 mm mesh sizing. And then this one will be a different case where we will be using mesh control, where we only actually change mesh at a certain area. So it is 1 mm plus 0.5 mm for the last case. So now I'll be skipping to the demo. The result will be what I'll be discussing right after I finish my demo with you. So if you actually scan the QR code and access the Google Drive, so this is the file that you will be looking at, the lever. So once you click on it, this is what you get, the lever, the 3D model. So like I mentioned just now, we'll be focusing on Autodesk Inventor Nastran. But what you see right here is my app. I'm using Autodesk Inventor Professional. So previously, Nastran used to be a separate app, but right now it is actually integrated into Inventor Professional. So if you click on environment right here, you can see that the Autodesk Inventor Nastran add-in appears right here. This add-in will only appear if you actually downloaded the Autodesk Inventor Nastran add-in from your Autodesk website. Do also note that if you like to download, make sure that your Autodesk Inventor Nastran is of the same year with your Inventor, the main app, the Inventor app. So if your Inventor is of the year 2021, please make sure to download Autodesk Inventor Nastran 2021. You also do not have to worry that you are using a 2022 version because the interface and the result will not differ that much, or it will be actually quite similar to that of 2021. So I'll begin right now. You can just click on the Autodesk Inventor Nastran if you are following along. So let's wait. It takes a bit of time to load depending on your PC capability as well. So like I said just now, first we have our idealization step completed. So we will be doing boundary condition. In the second step, like I said just now, there are 4 conditions you need to apply. The first will be applying material to your 3D model. So how do you do that? Right here, you see at your browser, we call this the browser. So at your browser, when you click on the plus sign at your solid, you see that the material applied to your solid is a generic material. So now we want to change the material. In order to change the material, you have to right click on the generic, click on edit, and you will come across this add-in. So this allows you to change your material. I want you to change to mild steel. So you click on select material. Then you will see that you will actually have the option to go through the Autodesk material library or the Inventor material library. So for the sake of consistency, especially those who are following along, let's go through the Inventor material library instead. But actually they are pretty much similar. And then you scroll all the way down, find mild steel. So this is mild steel. As you can see, the material property has been changed. So to confirm it, just click on OK, and the material will be changed. The material property has changed. But I do not want to use mouse steel. I want to make a little bit of changes to the material. I want to do, let's say, a custom material. So just to rename it to prevent confusion, I want to change some properties right here. So that's why I'll be changing the name. So before I change the material property, let me tell you which property I'll be changing. The material property are as follows. So I'll be changing the elastic modulus, the Poisson ratio, and also the yield strength. So let's start off with the elastic modulus. So right now, for mild steel, it is 2.2 to the power of 5 megapascal. I want you to change it to 2 to the power of 5 megapascal. And for Poisson ratio, I want you to change it from 0.275 to 0.29. And finally, the yield strength from 207 to 200. So in case if you miss what I've said just now, I'll repeat myself. I'll be changing this, the elastic modulus, to 2 to the power of 5, the Poisson ratio to 0.29, and finally, the last and the third and the last, which is the yield strength to 200 megapascal. Click on OK to confirm your material change. So right now, if you click on a plus sign, you see that, oh, the material has changed to still your custom material. So that is the first step in your boundary condition. The next boundary condition you are supposed to apply is constraint. Let's go back to the slide just now. And let's look at the scenario right here. So your 3D model is placed into this machine, and the constraint, if you look at this slide, they actually indicate that you have two pin constraint. The pin constraint at the top and at the bottom right here. You have to notice that it is on the longer end of your lever. So at this opening and this opening will be your constraint or fixture, in other words. If you look at the 3D model, right now it is not in the right orientation. So you want to rotate it. In case, for those of you who are actually new to Autodesk products, you hold on to the shift key and click on your scroller. You hold down onto your scroller of your mouse, you are able to rotate your 3D model as such. Besides, you can also rotate from this side. So let me correct the orientation. So this is what it looks like in the slide. So first put in this orientation, and we know that this part and this part will be your constraint, the part that is fixed. Click on the drop down arrow, and then you click on pin constraint as seen in the slide. I want you to also rename the constraint. So for the first constraint, let's apply to this part. Renaming is actually quite important because let's say if you make an error, it is easy for you to refer, oh, which constraint to look at and to edit. If you leave it as constraint 1, you need to go through one by one to see where is its location. So now I rename it to center pivot, and it is for this constraint right here. Let me now select the face. So select entity stands for selecting the face that you want to apply constraint to. So I'll be selecting this inner face. Make sure you select the right face. It is the face highlighted in blue. And then you click on preview. So preview, or this spectacle right here, actually allows you to look at the forcing, the constraint forcing that is applied to your structure. So now for the center pivot, click on this preview. You can see that, oh, the constraint is actually not, the preview is not that clear. You can just adjust this display option right here and change the density and size so that it is better illustrated. Do also note that when you change the sizing and density, it will not affect your result in any way because this is all for the sake of illustration purpose only. So you can change and play around with the size and density just to look at how the constraint is actually applied. It will not change the magnitude and such. So click on OK to confirm the center pivot. So next, you are applying the second constraint. The second constraint right here, the upper one. We assume that right now, it is actually acting on the upper surface. So similarly, it is pin constraint as well. But this time, Let's rename it to slot pivot because it is a slot. Compared to the previous one, it is a slot this time. So for slot pivot, let's assume that now the constraint is applied to the upper surface. The upper surface I've selected. Right there, the part highlighted in blue, the upper surface of this slot. And then similarly, you just click on the preview and change the setting to look and see whether your constraint has been applied to the correct area. So we assume that it is acting on the upper surface. So this is how the illustration is. Click on OK to confirm your second constraint. So as you can see in the browser right here, your constraint of center pivot and slot pivot has been applied. So why I say renaming is important is because later if you actually need to make an edit, renaming actually helps you to be more efficient. So now we have finished applying material and applying constraint. The next boundary condition will be applying force or loading. So you click on loading. Let's go back to the slide just now. So you can see that at this end, the weight is acting at the shorter end of the lever, the shorter end. This is the shorter end, this is the longer end. The shorter end here, you can see that weight is acted downwards at this end. So that's what we want to do to we want to simulate on our 3D model as well. Let's rename this one to slot pin load. Let's make it pin load. It can be, the naming can be up to you, whatever you think that can help you identify easily later on. So I want you to assume this time around the weight is acting on the further end surface. I want you to assume that it is acting on this surface. So since it is a curved surface, it is more appropriate to select the right forcing for it. So in this case, it will be bearing load. Since it is on a curved surface, I think that bearing load is rather appropriate for this case. If you click on preview, you will not see anything. Why? It's because you haven't applied the magnitude to it and the direction. So if you look back at the slide, weight is acting downwards in this direction, downwards. So if you look at the coordinate system right here, we know that weight is acting in the negative x direction. So at fx, let's give it negative 30. So right now you can see that, yeah, it is actually applying on the correct surface. The illustration shows correctly, but we know that weight only acts in one direction, which is downwards. Right now, it is actually radially acting to the surface. So instead of normal to the surface, I want you to change it to component. And this will correct the direction of it. And now it is acting downwards in one direction. Click on OK to confirm your loading. So you're almost done. You're almost done with your boundary condition. So next, you click on the last step, which is the initial meshing. Change the size to 2 mm and click on OK. So this will generate a 2 mm mesh for you on your 3D model before you run your simulation analysis. So in case this is not actually the tetrahedral meshing, this tetrahedral meshing is not clear to you, you can change the color. Right now it is green. You can click on the square box, the color sign right next to your solid, and click on the color that you think will give you better clarity. So I'll choose black, and I think that this actually gives me a better view of how the meshing is. And then right now, we have finished the boundary condition. We will move on to the simulation. So you click on Run Analysis to execute your simulation. So for a 2 mm meshing size, it will not take as long as the later analysis that we will be doing, such as the analysis 2 with 1 mm and analysis 3 with 0.5 mm meshing. So now the simulation has been completed. Click on OK, and then it will show the result. Since we are focusing on 1 meter stress, you can see right here that the maximum stress applied onto your material, onto your product, your 3D model is 8.693. If you recall just now, your yield strength is 200 megapascal. So 8.693 megapascal is way below 200 megapascal, and you know that your 3D model will not fail from yielding. So do also note that if you look at this structure right here, the deformation has been exaggerated. There is no way that with such deformation, your product is actually still not under critical state. Like it should actually fail if your deformation is such severe. So if you want to look at the actual deformation, you just right click at any of this your result right here, any of it, click on edit, and then you will see something that shows you the setting of all your results. You click on the deform option and you see right here, deformation scale. Your deformation has been exaggerated by 10%. If you click on actual, look at your model. This is the actual deformation. If you actually change your setting to the actual deformation, it will not be visible to the eye how your deformation will actually act like. You will not know in which direction it will actually deform and so on. So let's click on cancel so that it does not apply the actual. Okay, let's change back to percent. Give it the original 10%. Now, see, we have finished analysis 1 with 2 millimeter mesh sizing. We will carry on with analysis 2 and analysis 3, and what we will change is only the mesh sizing. Everything else in the boundary condition will remain the same, such as the material, the constraint, and the forcing will all remain the same. So how to create a new analysis? We have finished analysis 1. To create a new analysis, you click on new, or you can duplicate analysis 1. So I'll show you both ways. So for analysis 2, let's duplicate it. The downside of duplicating an analysis is, first of all, let's rename to analysis 2 first. I'll show you in a moment. If you click down on your model, it actually duplicates all the constraint, loading, idealization, and so on. It actually duplicates everything and make your browser a little bit untidy. So that's the downside for duplicating an analysis. But the thing is, the good thing is, it actually automatically applies the previous loading, previous constraint, and including the idealization, which is your solid and the material applied. So everything has been applied accordingly to the analysis 1, exactly the same, including the mesh. But like I said just now, we want to remain everything the same and just change the mesh sizing to 1 millimeter. We are trying to find the optimal mesh sizing for our 3D model. So click on OK to confirm your mesh. And if you look closely, the mesh sizing will actually decrease in size. Once it is completed, you can see the mesh sizing has been decreased. So click on run to actually simulate, and we will look at the result. We will look at the result difference. Since this time it is of a smaller meshing, the time to simulate will be much longer than the previous one with 1 millimeter mesh sizing. You will notice that in Inventor, it will show you the process of simulation and it might be untidy at times. If you compare to Fusion, it will actually hide the process in the background. And so it's actually less untidy as compared to Inventor. Sometimes too much detail can be confusing to the users. So now the simulation has been completed for the second analysis, where we only change the mesh sizing. So because we changed a setting in the displacement just now, so now it actually by default, it changed my result to displacement. If you want to look at the 1 meter stress, just double click on the 1 meter stress and it will show you the stress result. So just now it is 8.6 or 8.7 and right now it is 9.271. So we will continue doing meshing until we actually get to actually plot a set of data and see that which mesh sizing is actually the optimal mesh sizing. So now we will continue and reduce the meshing with a new analysis. So this time I want you to click on new to create a new analysis instead of duplicating. Click on new, click on OK to create analysis 3. So what you can see from here is, yes, it does not create so much clutter. It did not create duplicate again if I actually click on duplicate, you will have a new copy. So if you click on new, what you have to do is you have to manually bring in all your boundary condition from the previous one, such as your idealization. You have to drag from the bottom model back into the idealization here. Similarly, with your constraint, you have to apply, since you want to apply the same constraint and only change the meshing, you have to drag up the constraint into your analysis. So we drag the center pivot up, the slot pivot up. So we are applying the same boundary condition. Similarly, with the load, we want to drag the pin load into your loading. So now you actually applied the same boundary condition to your analysis. Everything is similar. The material is same. Everything is same. The loading is same. Constraint is same. We just want to change the meshing. So now you click on the mesh setting. This time around, similar to the previous analysis, you click on 1 millimeter, but I want you to change something in the setting. I want you to change to 1.1 for max element growth rate. I will come back to this later. Click on OK for the mesh to generate first. Once it is complete, actually analysis 2 and 3 have the exact same setting if you ignore max element growth rate. It has the exact same setting. The changes is what I want to show you right now. So you click on mesh control. Mesh control allows you to change a mesh at a certain area. If you change the mesh of your entire 3D model, you're wasting a lot of time. You know that your critical area from the previous two results. You know from the previous two results that your critical area is this region. So you click on face data. Since your area is not a vertex or since it's not a vertex or a point, you just hover over this side so that you can select a face. You click on this face. We know that this face is the critical area. From the previous result, both of the analysis shows that the maximum stress is at this area. So you only just change this area, the meshing at this area will be sufficient instead of changing the whole model. If you change the whole model, you will compromise a lot on time and your running time for your simulation. Click on as you can see, I changed the meshing to 0.5 to reduce it from 1 millimeter only at this area. If you click on OK, you see, oh, there's no changes at all. So this is mesh control. Mesh control will not execute the change in meshing until you click on generate mesh. So you have to manually click on generate mesh for this part to change from 1 millimeter to 0.5 millimeter. Look closely and you'll see the reduction in mesh sizing. As you can see, the part further away from this critical area has a bigger mesh sizing. And at this area, it is of the size 0.5 millimeter now. I want to go back to what I said just now. I changed the maximum element growth rate to 1.1. So what this does is it actually helps to widen the transition between the big mesh to the small meshing. So 1.1, the lower your maximum growth rate value, the greater the transitional area. So you actually give a greater transitional area for it to transition from 1 millimeter to 0.5 millimeter at the critical area. So you click on OK to, just click on OK. Now we want to run the simulation. This time it will take a bit longer than the previous simulation with 1 millimeter mesh sizing for the entire 3D model, but it will not be as long as if you actually change your whole 3D model to the size of 0.5 millimeters, since we are only changing at the critical area. We know that changing at this area is sufficient since the previous two results show a consistency that this area actually suffers from the maximum stress and has the most highest risk of failure. So selecting mesh control actually helps you to save time and help you to find your optimal mesh sizing quicker. So now we will actually look at the result. So it actually only increased a bit from the previous one. Previously it was 9.2, now it is 9.726. I will not be doing analysis 4 with you due to the time constraint, and I will be moving straight to our result and show you what is the significance of doing so many mesh sizing. So if you look, the first analysis, with 1 millimeter mesh sizing, we get a result of 8.693 megapascal maximum stress at this area. And then with the second analysis, we reduce the mesh sizing from 2 millimeter to 1 millimeter. And then we get a result of 9.271 megapascal of maximum stress. For the third analysis, we remain the main meshing at 1 millimeter, but we only change the critical area right here to 0.5 millimeter. And then we get a result of 9.726. So for the fourth analysis that I did not go through with you, the only difference between analysis 4 and analysis 3 is at the critical area, I change from 0.5 to 0.25. So every analysis, I reduce the mesh sizing by 50%. So what pattern do you see from here? 8.693 for the first analysis to an increase of 9.271 in the second analysis. And then you get a difference of 7%. From analysis 2 with analysis 3, you get a difference of 5%. And analysis 3 and 4, you get a difference of 1.8%. So what this shows you? This shows you the convergence of mesh. When you reduce your mesh sizing, it shows you a convergence of your result changes. So you know that, let's say, for example, I were to do analysis 5, and I reduce the mesh sizing to 0.125. But let's say I only get, for us, we assume that we only get a result of 9.91 megapascal. So it is actually insignificant for you to actually do reduce the meshing and get a result that only shows you a 0.01 megapascal difference. So from there, you know that the analysis that the mesh sizing, the optimal mesh sizing is the fourth analysis with 0.25 millimeter mesh sizing. So one more thing I like to say is, if you actually want to know whether your simulation is correct or not, you just have to reduce the mesh sizing. And if you see a pattern of convergence, means it is a good sign that everything you applied in your boundary condition is correct. So when you see convergence, it's a good sign that your simulation has been done correctly. So this is the significance of mesh convergence, which is the focus of our topic today. I'm so sorry that I actually go a little bit over time, and I thank you so much for staying up until this point. One last thing I'd like to ask from you is, if you go to our page, acadsystem.com, and you scroll all the way down, I would truly appreciate if you actually follow us on YouTube. You follow us on Facebook and subscribe to our YouTube channel. It will help us a lot in growing our company. Thank you so much. And this is the end of our FOL, our free online lesson.